Today we're going to talk about Merlin, Shopify's new machine learning platform. This nice visualization image is from our engineering blog post about Merlin that we published a few weeks ago. And I was already introduced, but a little bit about myself. I'm Isaac Vidas. I'm a tech lead on the machine learning platform team at Shopify. Joined Shopify last year in March. And as you heard, I love distributed systems, MLOps, and emojis. And yeah, I love the heart emoji hand, Chris, just FYI. I'm very happy to connect on LinkedIn and chat more about MLOps or whatever. And so just for anyone who is not familiar with Shopify, Shopify is an all-in-one commerce platform that enables merchants to set up online shops easily and make commerce better for everyone. We're all on the same page now. Now that we know more about Shopify and about me, let's talk more about machine learning at Shopify. And so at Shopify, we have hundreds of data scientists, tens of teams that are doing ML and machine learning and working on machine learning related use cases. Many data scientists are already using Merlin, and the migration to Merlin, our new ML platform, is ongoing. And so in the ML platform, and as a whole, our goals is to enable Shopify's team to create the whole machine learning workflow and to enable our data scientists to train, test, deploy, serve, and monitor machine learning models efficiently and quickly. And so with Merlin, we want to enable scalability for our users with robust infrastructure that can scale up to our machine learning workflows. We also want to enable fast iterations with tools that reduce friction and increase productivity for our data scientists and machine learning engineers by minimizing the gap between prototyping and production, as well as flexibility so that our users can use any library or package that they need for their use case. And so now that we know more about machine learning at Shopify, let's talk about Merlin specifically and how we built it. As a background, the machine learning platform at Shopify went through 2 iterations in the past. And it took a few years to get to where we are. The first iteration was built on top of an in-house PySpark solution, which is a legacy system that we use at Shopify. Because of different requirements, we started working on a second iteration a few years back, which was built on top of Google AI Platform, which is a managed service on GCP. And then last year, we started to reevaluate our machine learning platform requirements based on what we had a vision for the future and also based on new requirements that we got from our users. And we decided to rebuild our machine learning platform on top of open source tools and technologies around the goals with the focus on the scalability, fast iteration, and flexibility that I mentioned before. The timeline for building Merlin started back in March 2021, where we made a decision to rebuild the platform. In April, we started prototyping with different tools and technologies. And then in August, we started building the actual production platform. In early February 2022, we released Merlin as a general availability to all of our users. Now, you see here the timeline and the journey, but obviously the work is never done. We do recognize that there are still gaps in what we want to have at the end and what we build, but it is production ready and users start to use it with the real use cases. This is a diagram, of the early vision for Merlin. Back then, we didn't even decide on the name yet. And so here we can see a very, very high-level design that obviously doesn't capture all the parts, but it basically shows the input data starting from our data lake with the data sets that are flowing into our machine learning workflows, or the streaming events that are coming in from the pipelines. In the machine learning workflow, we have the different steps, such as compute, training, evaluation, hyperparameter tuning, and then serving the model for batch jobs or for online inference. The predictions that comes out of it can go into the Shopify core services that are user-facing. And then this whole workflow and this whole system runs on top of Kubernetes as the infrastructure level, and on top of Ray for the distributed computation to allow us to scale up and use different integrations and libraries on top of it. And this guy here that you can see is actually the Shopify logo with a beard, glasses, and a hat. This is what happens when you do not have graphical designers in your team. But we got it figured out. And so before we dive into the actual machine learning platform, let's talk a little bit about Ray, and just so we can all speak the same language. So Ray is an open source framework built by Anyscale. It provides a simple universal API for distributed computation, and it's used to parallelize machine learning workflows. It has many integration tools and libraries that are dedicated to ML. These integration can include XGBoost, PyTorch, TensorFlow, MLflow, Hugging Face, and many, many more. In addition, you can run different distributed processing libraries on Ray, such as Dask, Spark, or Modin. They even have a new integration that they're prototyping with Beam. This shows the flexibility and size of the Ray ecosystem. And then with Ray, Python is a first-class citizen, which is extremely useful for our data scientists that use Python on a day-to-day basis. You install Ray as any other Python library with pip install. And when you write your code, you start by importing the Ray library package and then run ray.init. Ray.init creates a new Ray cluster or connects to an existing one. The code that is running the ray.init and the computation work that is then being distributed across the cluster is called a driver in Ray language. This is an example of a Ray cluster architecture with a head node and two worker nodes. On the head node, we see the driver that is working, the driver that we just described, and it distributes the computation work across the different workers on this cluster. Each node, head node or worker, contains a Raylet, which includes the scheduler for scheduling the tasks, as well as the object store for the shared memory. The head node contains also the global control store, which keeps the metadata for the Ray cluster. Every time you run ray.init or create a new Ray cluster, it immediately creates a Ray dashboard dedicated for that Ray cluster. And so this dashboard is being used to see the state of the cluster and the running jobs on top of it. In here, you can see different parameters such as the CPU, memory, GPU, and Plasma, the shared memory store, utilization. You can also see a view of all the different hosts that are running on the Ray cluster, as well as the different processes that are running on each host individually. And for each one, you can see its own utilization and related logs. This is very, very helpful for debugging and to do resource optimization on the cluster. This is a very simple Ray program. We start by initializing the Ray cluster, and then the function that we want to distribute across the cluster, in this case, it's a very simple function that we call f. We decorate with the ray.remote decorator. Then we spread the work around the cluster. That is being done automatically. And we call ray.get, which is a blocking call, which collects all of the results back into the driver so it can print them. Two primitives that are important to recognize in Ray are tasks and actors. A Ray task is basically a Python function, like we just see. And then we just decorate it with the ray.remote. And a Ray actor is a Python class that, again, we decorate with the ray.remote. The main difference between them is that while task is stateless, actor is stateful. This is an example of training a model with an XGBoost model with Ray. And I'm not going to dive too deeply into this example. This is a pretty standard XGBoost model training. And so the only difference here is that we use the XGBoost Ray package, which wraps the XGBoost package. And then inside of the training function, we include the Ray params parameter, which can specify the number of actors, and for each actor, the number of CPUs or GPUs that we need in order to distribute the work. And so when thinking about a machine learning platform that runs on top of Ray, or has Ray as part of it, there are different ways to build one. One thing to recognize and remember that with Ray, the driver and workers must have the same Ray version and same Python version. This is because of the serialization that is being done into the shared memory. One way to build a platform around this is to say that we have a single Ray cluster to rule them all. So one Ray cluster that all of the machine learning workflows can run on top of. This means that the requirements for each machine learning workflow that runs on top of that single Ray cluster has the same Ray version and the same Python version as the Ray cluster, right? So this is a bit of a limitation for some use cases. The other way is to have many Ray clusters where you would have a Ray cluster dedicated per machine learning workflow, which means that you can isolate your machine learning workflows and Ray clusters and have a dedicated Ray cluster per use case. So you can keep a separate version of Ray and Python and maybe even the different libraries that you use between your different use cases that are running. For our machine learning platform, we decided on having ephemeral Ray clusters. So each Ray cluster is created when the job starts and deleted when the job ends. Each Ray cluster is isolated for a specific machine learning use case. When you build your own platform, you can also decide on a different way and method to do it, because there's a lot of ways to build it and there's a lot of flexibility in it. In order to keep these Ray cluster isolated, we decided to wrap them into a concept that we call Merlin Workspaces. And so a Merlin Workspace is a dedicated environment per use case that allows our users and use cases to have a requirements from the infrastructure layer up to the application layer. And so in here we see 4 different examples of machine learning use cases, and each one can contain different requirements on the Kubernetes level and then on the application level. For example, the product categorization workspace requires GPUs as well as CPUs. And on the application level, they can use their own dedicated Ray cluster with the specific libraries that they need for the training. For example, TensorFlow and Ray Train. Other use cases might have other requirements and other infrastructure Kubernetes resources. If we take a step back and look at the architecture as a whole, the Merlin core is what we just saw with Merlin Workspaces. And it runs on top of Kubernetes, has auto-scaling that it can leverage, and so each Merlin workspace can scale up to the requirements that they need or to the load that they should run on. Each Merlin workspaces individually has a Ray cluster, and in that Ray cluster, they can run the whole machine learning workflow or a subset of that workflow. And so in this Merlin core, in that box, we can see the scalability, the scalable ability that we can give to our users. Each Merlin workspace can also access our feature store, which we call Pano, for features, and our data lake to extract, to load data sets or models or to save new models that we just trained. And then in order to manage all of these Merlin workspaces, we have created and built a dedicated API, which we call the Merlin API, which every client that is using our platform goes through. It's a unified, centralized API. And so if a user prototype from a Jupyter notebook, they go through the Merlin API to create these environments that they need. And then when we orchestrate the production machine learning workflows from either Airflow or Uzi, they also go through the Merlin API to create the Merlin workspace for their work and to delete it later on. This just shows the fast iterations that can happen between prototyping and production. So the user from a Jupyter notebook can already create that scalable environment and the Ray cluster and Merlin workspace that will later be used in production. This is an example of a payload that we send to the Merlin API in order to create a new Merlin workspace. It includes parameters such as the max age for a Ray cluster or for a Merlin workspace, the name for it, so it can be identified, the owner, so we can tag resources and perform cost analysis later on, the image that is being spun up in the different pods, as well as the min and max workers for auto-scaling, and the CPU memory utilization for each individual node. It can also include different parameters that we didn't include here, such as GPUs type and number of GPUs, etc. This REST API was built on top of Fast API. It's, again, Python. And it's a centralized API that all of our clients work against. Just want to highlight it again. If a user wants a Jupyter notebook to be available immediately with this workspace, they can also add this flag, and this will be done automatically for them and make it available for them. This API and all of these parameters, behind the scenes, what is happening is that we just take them and inject it into a YAML manifest, a Kubernetes manifest, which is then being run through a kubectl apply. Right? So all of this API is just a fancy kubectl. This allows us to abstract all of the Kubernetes complications from our data scientists and users. And it also allows us to reduce the amount of different permissions that we need to give for different servers and environments. This API is also versioned. So when we make a change to this API, the clients can still use the last version as it will be backward compatible. When you create a Merlin workspace, you get back a lot of details about it. These details help the user to monitor and to work with the Ray cluster and Merlin workspace that they just created. Some of the URLs that we return back are the Ray dashboard that we just saw for optimization and debugging, the Ray head URL, as well as the Ray job submit URL that allows the users to connect remotely or to run jobs remotely on the Merlin workspace, a Jupyter notebook URL if the user actually added that flag to enable it, and observability URLs with Datadog metrics and Splunk logs. So each workspace has a Datadog dashboard with its own metrics individually, so they can see their different utilization as well. And then each Merlin workspace contains a time to live and an expiration time. This is very helpful in order to make sure that we don't have zombie workspaces staying up for longer than needed. And when the expiration dates arrive, an automatic periodic job runs through and deletes these workspaces and return the resources back to the Kubernetes cluster. In addition, we also include the head and worker and Ray operator pods details in order to easily debug different issues with events. Once we have our Merlin workspace up and running, there are different ways to connect to it and to run different Ray jobs from different clients. For example, if a user works from a Jupyter Hub and a Jupyter Notebook, the driver that they're running is basically runs on their notebook. That notebook can connect to a remote Ray cluster over gRPC and use the Ray Client API to run and distribute different work. From Airflow, when we run a new workflow or a new DAG, there's the Kubernetes pod operator that spins up a new pod where our driver is running on top of it. And that driver, again, connects with the Ray Client API over gRPC into our remote Ray cluster. And then from our legacy PySpark system, which runs with Python 2.7, we have the Ray job submit, which runs on top of REST API that allows us to, again, run a Ray job on our Merlin workspace, but this time the driver runs on the Ray head node, and then distribute the computation internally on the cluster. This just shows like the many different clients and many different ways that we need to support different jobs to run on top of our Merlin platform. When looking at the Kubernetes level, there are a lot of components and different parts that we have to create when we actually create a new Merlin workspace, and the way that we isolate it from other workspaces as well. And so when we create a new workspace, we create a completely new Kubernetes namespace in our Kubernetes clusters. On top of it, we start by creating the Ray namespace operator, and that operator is responsible for starting up the Ray cluster, as well as auto-scaling that cluster across the Kubernetes. And then once our cluster is up and running, we have two ingresses, one for HTTP access for the dashboard or Jupyter notebooks, or to run Ray jobs, or an ingress for gRPC to connect through the Ray Client API. Obviously, this whole diagram doesn't include everything that we put there. There are also services accounts, certificates, and different Kubernetes resources that we create that are not included, but this is a high-level overview of that. When the Ray cluster starts and the Ray workers, each one runs a pod with a specific image that we built beforehand. The user, when they write their own machine learning workflow, they create their code and push it into GitHub. Automated CI/CD pipelines then take that code and turns it into a Docker image that is then being pushed into the Google Cloud Registry, GCR. When the pods start, they also pull that image from GCR in order to use the same environment for the Ray head node and the workers. This screenshot is basically a Merlin project that a user creates on Merlin. We have a monorepo with all of the different Merlin projects on top of it, and each Merlin project gets their own dedicated folder. Each folder contains the source code in the SRC folder, tests, and configuration inside of this config.yaml. When the user pushes a new branch or merge a PR into the main branch, automated CI/CD pipelines take that version of the code and create a Docker image specifically for this project. This is an example of a configuration for a Merlin project. What do we include in it? We include the name of the code owners or the group, and that group is basically the team that owns this code and maintains it. We also include the base image that we build the new Docker image on top of, as well as different packages that we want to install on the system level. Each Merlin project comes with a Conda environment that the user can specify their own Python version and specific machine learning or Python packages and libraries that they want to install. In this example, the user decided that they want Python 3.8.12, Ray version 1.12.1, and they want to include pandas, numpy, and scikit-learn for their machine learning workflow. This shows how flexible this type of solution is, because each user can decide on what they need to use in order to, like, the best tool that they want for their use case. In order to enable better access to Merlin and the different tools that we created, we had to make sure that the user experience for our data scientists is up to speed with everything that we build. In order to do it, we created a Merlin CLI, which allows our users to manage their Merlin projects, manage their workspaces, create local dev environment for local testing, as well as the ability to easily extend it as things move very, very fast, and we include more and more features as we go along. In this picture here, screenshot, this is an example of how a user can create a brand new Merlin project in our system. And so they run Merlin projects create and the name of the project, and immediately they get a wizard that they can select the machine learning libraries that they want to include in their configuration. If that machine learning library is not here in that list, then they can start with nothing and then put everything in their config.yaml file. Once the user is done and productize their code, they can go ahead and start to orchestrate what they created. This is an example of a very, very simple Airflow DAG, where we start by creating the workspace for the work, go into the training phase, and then delete the workspace at the end. If anything happens during the training and something fails, we still delete the workspace at the end in order to reduce the amount of resources that we waste and return the resources back to the Kubernetes cluster. For each of these steps, we created a specific operator that can allow and abstract the user from actually writing all of this code themselves. So they can focus only on the machine learning part of it. If we look at the user workflow end-to-end, the user starts with a brand new machine learning use case where they create a new Merlin project in that monorepo that we talked about. Then they go into the prototype phase where they create a Merlin workspace and start to prototype their use case from a Jupyter notebook. Once the code is ready, they can go ahead and put that code back into Merlin project code and then merge it into the main branch. And then they can go and orchestrate a DAG or an Uzi flow in order to schedule their work so it can run periodically. When the user needs to enhance or include new features in their project, they go back into the prototype phase and iterate on their project again. So, now that you know how we built Merlin, let's talk about some lessons learned from that process. When building a new machine learning platform, it's important to build around real use cases in order to make sure that real user requirements are addressed. In our use case, we started by taking one of the most complicated and largest use cases that we had at Shopify. That includes image classification, embeddings for text and images, and a lot of data that passed through it. And so it allowed us to validate everything that we built very early on and make sure that the tools and technologies that we started with can scale up to what we needed. For example, Ray. It's also important to prioritize the right requirements and to make sure that you're not tailoring your machine learning platform to a specific use case. So having one use case is great, but you should probably have more than that. While there are a lot of vague terms and shiny features, it's important to try and make sure that you build for the long run. Technologies can change, but some concepts can be considered early on, such as not wasting resources, having cost analysis, etc. For example, making sure that each workspace has a time to live at the end, and it can be deleted automatically, was very important for us early on, just to make sure that people will not end up spending a lot of money on wasted resources. Another part was to make sure that when we build the new use cases, a user can decide on the type of libraries that they want to include. So they can early on make sure to use that flexibility. And while building, it's also important to remember who your users are and their profile, and if required, create a CLI or create different tools to reduce the barrier of entry and to make it easier for them to enter your platform. While building a new machine learning platform, there's a lot of decisions to be made that require balancing between different requirements. In larger companies, there are probably legacy systems that would require integrations. Some of these might introduce tech debt, so it's important to decide early on how much time you need to invest in these versus in new features for the platform. For example, the legacy Python 2.7 that I mentioned before is a system that our users use on a daily basis for doing data modeling. And data scientists just have to start building from that. So early on, we decided that we must invest in integration with that system in order to enable our users an end-to-end workflow. It required a lot of time and a lot of effort, but from where I'm looking right now, it was definitely worth it because now our users can actually utilize everything we built for them. There's also a balance to make between creating an opinionated workflow for users versus giving them freedom to choose their own adventure. There are pros and cons for each. For our machine learning platform, we chose to be less opinionated, so our users can use any machine learning libraries that they want. But that freedom has a cost because now they own these requirements and they need to make sure about upgrading the different packages and make sure that they don't have conflicts between them. Building a machine learning platform can take a while. During that time, there are org priorities that may change, and different use cases or requirements might become more important. It's good to keep a good buffer for these changes. Last year, at some point, they introduced the new M1 laptops at Shopify, and so we had to make sure that all of our tools can support the M1s, so our users can actually start using it. And during the build, there are a bunch of skills that are required across the stack, from DevOps to back-end engineering to front-end engineering and user experience folks. So it's important to keep a good balance of these skill sets in the team and also outside of it. Building a platform is completely different than maintaining a platform. And so when you're building, you have to move really, really fast. You can break things, everything is completely fine. And then you release your platform and you go into sort of like a maintenance phase where you're still building new things, but you have to keep and make sure that your platform is stable as well. So you move between, convincing that things work into convincing that things are stable. When you go into that maintenance mode and you want to include new features, that's where you have to move a little bit more carefully and make sure that you don't break things, or you need to schedule downtime for the users, etc. In addition, all of these technologies that you're using are great. Like again, Ray, it's a great library, but it changes and there's a new version every month or so. When that version comes out, we want to include and incorporate it into our platform and make sure that we use the new features and new fixes. So in those situations, we have to move fast and make sure that our users know about all of these new capabilities. Onboarding new cases requires additional effort and can be time-consuming. So once you release your platform, having a dedicated team or dedicated group of people that are doing that specific thing and helping other teams to onboard and make sure that they know how to do the things that they do is super important. As more users onboard to the platform, there will be new requirements which you need to plan for in your roadmap. So building a platform is hard, maintaining is hard, and also if you already went through 2 iterations of building a machine learning platform, you have to migrate folks, and migration is also hard. So after you build your platform, you will want users to start using it. It's important to invest time in documentation, tutorials, troubleshooting, end-to-end documentation that can help the users to onboard and to reduce the barrier of entry. It's much better if users want to move to the new system than have to move to the new platform. In our case, it's easier because Merlin enabled our users to do much, much more than before. So right now, it's pretty common when we talk to our users is that if they never heard about Merlin and they want to start using it, one sentence that I keep hearing is like, oh, it seems like we can do whatever we want on Merlin, which is really great for us to know because we don't have to do a lot in order to convince folks. But at the same time, we, as a machine learning platform and as the maintainers of that platform, we have to know where to draw the line. For example, we had a use case that was just trying to run Spark on top of Ray, on top of Merlin, because the iteration that they can do on it was much faster than with the legacy system. But at that point, we kind of had to understand exactly what the requirements are and why they need to do it. Something to consider is that newly onboarded use cases will add more immediate support burden on the team. So you need to figure that out as well and take that into account. Overall, if you have iterations or past iterations that in different platforms that you had before, it's good to have a migration plan and to execute it early on in order to reduce the amount of work that is being done on the legacy system and deprecate it easily and fast. We're almost at the end. So what did we cover? We talked about Ray. We discussed building a machine learning platform on Ray, how to isolate distributed computation environment, as well as lessons learned from building a machine learning platform. But wait, there's more. The gaps that I mentioned before, there's still a lot of work that we have to do. And so we identify different needs and requirements that are currently not included as part of our new platform, such as a model registry and experiment tracking, the ability to have a standard of deploying and serving machine learning models for online inference, monitoring ML as a standard solution on the platform, and low-code machine learning pipelines to abstract more code and more of what the user are doing and make sure that they are focused on specifically the machine learning parts of it. And so I wanted to just say acknowledgements and many thanks, and a huge, huge shout out to the ML platform team that's been working on all of these since last year. everyone at Shopify that helped us on that journey, from the data science teams that onboarded, the product managers, DevOps teams, and the user experience test group that helped us in the last 2 weeks before release to validate everything that we build. As well as a special thanks to the Anyscale team for helping us with anything Ray related along that process. And thank you for the MLOps world for actually accepting this talk and hosting this event. And to all of you, you've been a beautiful audience. So thank you very much.
Hi, impressive work. So given that you've gone through 3 iterations and a year plus of building Merlin, can you talk a little bit about your motivations and maybe constraints around choosing open source versus ready-made enterprise solutions like Amazon SageMaker and things like that? So given your challenges and success that you have, would you choose a different strategy building Merlin, or do you still feel that open source is the way to go?
Okay, so I guess I'll repeat the question and let me know if I got it right. Looking back, is it still worth putting a bet on open source technologies versus using a commercial solution based on the resources and the amount of work that it took?
Right. You did, in your second iteration, you did use Google API,
yep.
Right? So you've gone through kind of both directions. So I was wondering, what's your take?
So that's a really great question, and there are different aspects to it, and the ability to recognize even when do you actually need to create this new iteration, and why now? What is the momentum that you have right now that you can allow yourself to rebuild something? And maybe it's partly by looking ahead a few years and recognizing that, hey, we already have some limitations. And this can be with the technologies that we had at the time, and it can also be the way that we designed the legacy machine learning platform. And also, it has to do with new developments that are happening in this domain. And so you can also look at other large companies and how they built their ML platform and see that maybe they started at a time where there just wasn't a good enough solution out there to actually build on top of. Personally, I think building on top of open source technologies is a win-win for everyone because it allows the open source solutions to actually create a standard between multiple companies and this domain. And it also enable us, or me specifically as a machine learning platform maintainers, to recognize and make sure that I can actually support the machine learning platform, and it's not just like a black box that I just don't know what happens under the scenes, right? So again, I am pro open source solutions, and I think that if there is again a balance of how many resources and how large your team is and how much effort and time you can put into things, but it all comes into that calculation. So what's good for us might not be good for someone else. Thank you.
Awesome talk here. My question is, because the Ray cluster, I assume, provides a bunch of functionalities underneath, and it all runs on Kubernetes, and we all know how much operational overload can Kubernetes be with upgrades, with node rotations, cluster rotations, right? If we only require CPU and we don't require GPU for our computations, can we go serverless and have the same capabilities with Ray?
So in a sense, yes, right? It depends on if the API that the users are using can actually support that. But if we do get these type of requirements, we can do it, right? Again, Ray is one part of that. And if a user just needs to spin up a pod to run a very, very low hanging fruit, then they can do it.
I mean, serverless can scale as well, right? It's not like it is just a small computation that someone runs on. It's just CPU versus GPU, right?
Yep.
So if we just want CPU, it can scale to whatever we require? And is there a possibility to run Ray packages, Ray head, all serverless, is what my question is.
Can you repeat that? I'm not sure.
So right now, we are running Ray cluster on Kubernetes.
Yep.
Kubernetes road, right? Instead, can we run those same functionalities on Lambda or Google Cloud Function or just serverless?
Got it.
Without managing Kubernetes.
Yeah. Again, it depends on the type of work that you need to run, right? And then Ray is a good use case for it, but you don't have to use Ray. If I understood your question right, but if not, let's take it offline.
We can discuss it offline. Yeah, right. That's fine.
Hey, thank you so much for your talk.
Thank you.
At the beginning of the talk, you mentioned Spark on Ray, Dask on Ray, and Modin on Ray.
Yep.
But then when you showed the Merlin CLI, the user could only choose kind of like PyTorch or is there kind of like a default like parallel data processing engine that's included in all these images? And if so, like which one did you choose? And did you have a preference? Any trouble running those on Ray?
Right, excellent question. So yes, we do include some very basic packages, and we also have an internal package that we created, which includes some common parts and code for our users. We don't include by default Dask or Modin or anything like that. We do have the Ray dataset, which is the ability to do distributed pre-processing on top of Ray. So that's included as part of the Ray ecosystem. But if a user needs to use Dask or Modin or Ray DP, which is the Spark on top of Ray, they can include it in their configuration manually.
And did you run into any troubles with any of these or any kind of one that worked better than the others?
Yes, actually. So something to remember is that we started working with Ray back when it was like 1.4. Right now it's in 1.13. And so throughout that phase, a lot of things changed. Back then, we didn't even have Ray datasets. So our initial thought was to include Dask for this light pre-processing for our users. And yeah, definitely, there were some integration things that we had to work around, as well as the ability to make sure how do we create our data pipelines so they can fit well with what we want to run on the machine learning workflow. So if we need to partition the data set in some way or to shuffle the data, how do we do it? So there are some guidelines that we had to create and tutorials to allow us to do it.
Thank you.
Great, thanks.
Hi, thanks for your amazing talk. I have a question about when a workload fails, right, in your Ray cluster, do you actually have a concept of saving the progress of your machine learning workloads, or you retry, like let's say your job is running for a couple of hours and it fails, so you retry from the beginning, or there is a concept in your platform where you save checkpoints?
Yeah. Right now, so we do include some retries in the workflow, but it's not abstracted or integrated properly, but this is something that we work on.